You were taught that objective reality is one of those philosophical questions. The kind of question that sounds deep at a dinner party, but that physics itself does not take seriously. The kind of question that belongs to philosophy departments and late-night conversations, not to laboratories with lasers and detectors and six-figure grants. You were taught, or more precisely, you absorbed by osmosis from every science class and every documentary and every popularizer you have ever encountered, that reality is real, that what happened, happened, that if two people measure the same thing, they get the same answer, that facts are facts. That is the version of the story you were given. It is incomplete in a way that should disturb you. Before we dive in, if you want to support the channel and get exclusive content on all things space and physics, check out our Patreon. Link is in the description. In 2019, a team of physicists at Heriot-Watt University in Edinburgh built an experiment specifically designed to test whether objective reality exists. Not metaphorically, not philosophically. They tested it the same way you test any claim in physics, with photons, with detectors, with statistical analysis, and with a mathematical inequality that would be violated if observer-independent facts do not exist. They used 6 photons. They ran the experiment for 360 hours. 15 days of continuous measurement. They collected 1,794 6-photon coincidence events across 64 measurement settings, and the result came back at 5 standard deviations. For context, 5 sigma is the gold standard in particle physics. It is the threshold CERN used to announce the discovery of the Higgs boson in 2012. When the Higgs hit 5 sigma, it was on the front page of every newspaper on Earth. The President of the United States mentioned it. The physicists who predicted it won the Nobel Prize the following year. 5 sigma means there is roughly a 1 in 3.5 million chance the result is a statistical fluke. The Proietti experiment hit the same threshold, and you have almost certainly never heard of it. The paper was published in Science Advances, Volume 5, Number 9, September 20th, 2019. The lead author was Massimiliano Proietti, an Italian doctoral student. The senior author was Alessandro Fedrizzi, a professor of quantum physics who had trained under Anton Zeilinger in Vienna, the same Zeilinger who would win the 2022 Nobel Prize for Bell test experiments. The paper's title was Experimental Test of Local Observer Independence, and the result was clean. The statistics were overwhelming. The implication was that if you accept locality and freedom of choice, 2 assumptions that underpin essentially all of modern physics, then observer-independent facts do not exist. I need you to understand how specific that claim is. This is not reality is weird. This is not quantum mechanics is mysterious. This is the idea that the facts of the world, the outcomes of measurements, the things you write in lab notebooks and publish in journals and build careers on, may not be the same for every observer, not because of measurement error, not because of imprecision, because the fundamental theory of physics does not require them to be, and the part nobody wanted to say out loud was not the result itself. It was what the result meant for the thing they were using to get the result. If facts are observer-dependent, then the scientific method, which relies on facts being observer-independent, has been operating on an assumption that its own best theory says might be wrong. We will come back to that. It is going to get worse before it gets worse. The immediate question is how. How did do facts exist become something you can test with photons and mirrors in Scotland? And the answer starts with a man born in Budapest in 1902 who was so impossibly polite that when another driver cut him off in Princeton traffic, he said, "Go to hell," and then immediately added, "Please." Eugene Paul Wigner was born on November 17, 1902, at 76 Király Lutka in Budapest, then part of Austria-Hungary. His father Antal managed a leather tanning factory. His mother Erzsébet came from the Einhorn family. They were Jewish, but not observant, and they converted to Lutheranism after the political upheavals of 1919. I mention the conversion because Wigner's entire life would be shaped by the forces that made that conversion feel necessary. The wave of anti-Semitism and political instability that drove an entire generation of Hungarian Jewish intellectuals out of Europe and into the laboratories where they would reshape the 20th century. Wigner attended the Vasari Evangelicus Gymnasium in Budapest, a school so absurdly concentrated with future genius that it strains credulity. His mathematics teacher was Laszlo Ratz, a man who somehow recognized extraordinary mathematical talent in teenager after teenager. The boy sitting one class below Wigner was John von Neumann, who would go on to essentially invent the modern computer. The same high school, the same math teacher, two of the most consequential mathematical minds of the century, separated by a single year. Wigner studied chemical engineering at the Technische Hochschule Berlin because his father wanted practical credentials, but he gravitating toward physics with a force that could not be resisted. In Berlin, he attended the Wednesday colloquia where Max Planck, Werner Heisenberg, Wolfgang Pauli, and Albert Einstein were all in the same room. He befriended Leo Szilard, and he pioneered the application of group theory to quantum mechanics, a contribution so abstract and so powerful that the experimentalists of the era, unable to understand the mathematics and resentful that it worked anyway, christened it the Gruppenpest, the group plague. In 1930, Princeton recruited Wigner and von Neumann simultaneously. Wigner's salary was 7 times what he had earned in Europe. He anglicized his name from Gino to Eugene. His personal life carried tragedy that would shadow him for decades. His first wife, Amelia Frank, died in 1937, less than a year after their marriage. He later married Mary Annette Wheeler in 1941, and his younger sister Margit married Paul Dirac in 1937, after Wigner introduced them at a Princeton restaurant. The anecdote that survives from that introduction is one of the great stories in physics. When a colleague visited Dirac's home and expressed surprise at finding a woman there, Dirac, who was legendarily awkward in social situations, said, "Oh, I am sorry, I forgot to introduce you. This is Wigner's sister. Not this is my wife. This is Wigner's sister." The man had married a woman and still identified her primarily by her relationship to another physicist. I am telling you this not because it is charming background. I am telling you because the man who would eventually crack open the deepest fissure in the foundations of physics was not some fringe thinker working in isolation. He was central. He was embedded. He was connected to every major figure in 20th century physics by bonds of friendship, mentorship, family, and shared exile from a continent that was trying to kill them. During the Manhattan Project, Wigner co-drafted the Einstein-Szilard letter to President Roosevelt in August 1939, the letter that launched the American nuclear weapons program. He designed the full-scale Hanford production reactors for weapons-grade plutonium. He was there when Chicago Power 1 went critical on December 2nd, 1942. His reflection on that era was characteristically precise. "Thoughts of being murdered," he said, "focus your mind wonderfully." He held 37 patents related to nuclear reactor design. In 1963, Wigner won the Nobel Prize in Physics, awarded for his contributions to the theory of the atomic nucleus and the elementary particles, particularly through the discovery and application of fundamental symmetry principles. He shared the prize with Maria Goeppert-Mayer and J. Hans D. Jensen. Edward Teller said of him, "Eugene Wigner is so polite that he created the legend of Hungarian courtesy." By the time he retired, 27 laws and equations bore his name. And in 1961, 2 years before the Nobel, between designing reactors and proving symmetry theorems, he published a short philosophical essay that nobody took seriously at the time, that would take 60 years to test, and whose implications are still not resolved. The essay was called Remarks on the Mind-Body Question. It appeared as a chapter in a book called The Scientist Speculates, edited by I. J. Good, published by William Heinemann in London, pages 284 through 302. It was not a technical paper. It contained no equations. It was 18 pages of careful, almost reluctant, philosophical argument, and it contained a thought experiment that was going to haunt physics for the next 6 decades. Now, if you have heard of Wigner's friend, there is a good chance you think it is a variation of Schrödinger's cat, and I need to correct that right now, because the difference between them is the difference between a problem you can live with and a problem that threatens the foundations of how you know anything. Schrödinger's cat, proposed in 1935, illustrates the absurdity of quantum superposition at macroscopic scales. A cat in a box is simultaneously alive and dead until someone opens the box. And here is the misconception that even people who follow physics content online tend to hold. Schrödinger was not proposing that cats can be alive and dead. He was attacking the idea. He was performing a reductio ad absurdum. He was saying that if your theory implies that a cat is simultaneously alive and dead, your theory has a problem. The cat was never the point. The cat was the weapon Schrödinger was using to attack the Copenhagen interpretation. But here is the critical thing. The cat does not know it is in a thought experiment. The cat does not reason about its own state. The cat does not apply quantum mechanics to the system it is part of and arrive at a conclusion about what happened. The cat is a prop. Wigner's friend is not a prop. Wigner's friend is a physicist. Here is the setup, and I want to walk through it carefully because the details matter, and every step in this thought experiment carries weight. A quantum system can produce one of two outcomes. Wigner described it as seeing or not seeing a flash. Wigner's friend enters a sealed, isolated laboratory and measures the quantum system. From the friend's perspective, the measurement happens. The wave function collapses. The friend sees a definite result, flash or no flash. The friend records the result. The friend knows what happened. But Wigner, standing outside the sealed laboratory, has not interacted with it. And here is where it breaks. According to quantum mechanics, Wigner must describe the entire laboratory, the friend, the measuring device, the quantum system, all of it as a single quantum system that has evolved according to the Schrödinger equation. To Wigner, the measurement has not produced a definite result. The friend is in a quantum superposition of having seen a flash and not having seen a flash. Two observers, two descriptions, both following the rules of quantum mechanics correctly, and the descriptions flatly contradict each other. The friend says the measurement happened. I got a definite result. Reality committed. Wigner says the measurement did not happen. You are in superposition. Reality has not committed. Both are right. According to the theory, both are right. You might think the resolution is obvious. Open the lab and ask the friend. But that misses the point. Before Wigner opens the lab, before the two descriptions are compared, the theory gives two incompatible accounts of what is happening inside the laboratory right now. The question is not what Wigner will find when he opens the door. The question is what was true before he opened it. And the theory says both things. At the same time, about the same physical situation. This is not Schrödinger's cat. The cat does not have an opinion about whether it is alive or dead. The friend has an opinion. The friend has a definite experience. The friend saw a flash or did not see a flash. And quantum mechanics says that definite experience is real from the friend's perspective and is in superposition from Wigner's perspective. The facts of what happened inside the laboratory depend on who you ask. Wigner's own conclusion in 1961 was radical even by the standards of a field accustomed to strangeness. He wrote, "It was not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to the consciousness." And he went further. The very study of the external world led to the scientific conclusion that the content of the consciousness is the ultimate universal reality. Think about what he was saying. A Nobel laureate, a Manhattan Project veteran, one of the most rigorous mathematical physicists in the world. He was saying that the equations he had spent his career working with did not make sense without consciousness in the picture. That the friend's inner experience, the subjective awareness of having seen a flash, was what caused the wave function to collapse. That without a conscious mind observing, reality did not bother to commit to a definite state. This was not some New Age philosopher saying consciousness creates reality. This was Eugene Wigner, the man who designed the plutonium reactors, the man who proved the symmetry principles, the man with 37 patents and 27 eponymous laws. And he was saying the math required consciousness. And then, roughly 26 years later, he changed his mind. By approximately 1987, according to physicist Leslie Ballantyne, Wigner had reversed himself. He came to regard his consciousness argument not as a solution, but as a reductio ad absurdum. Not proof that consciousness was special, but proof that quantum mechanics' postulates needed revision. The thought experiment was not showing us something about minds. It was showing us something about the theory. Something broken. Wigner died on January 1st, 1995 in Princeton, at age 92. He had published his memoirs at 90. He was among the last of the Martians of science, and the question his thought experiment had raised, whether two observers applying quantum mechanics correctly can disagree about what happened, was no closer to being resolved than it had been in 1961. For decades, the thought experiment sat there. It was discussed in philosophy seminars and foundations of physics workshops, the kind of small, specialized gatherings where 100 people in the world care deeply and everyone else has never heard the question being debated. It seemed untestable. It seemed academic. It seemed safe. Then two people in Zurich made it unsafe. In April of 2016, Daniela Frauchiger and Renato Renner posted a preprint from ETH Zurich, that detonated like a quiet bomb in the Foundation's community. The original title was Single World Interpretations of Quantum Theory Cannot Be Self-Consistent. By the time it appeared in Nature Communications on September 18, 2018, the title had been diplomatically softened to Quantum Theory Cannot Consistently Describe the Use of Itself. But there was nothing soft about the content. I want to tell you about the people first, because the people matter, and the personal trajectories in this story tell you something the papers do not. Photons-Renner was born on December 11, 1974, in Lucerne, Switzerland. He is a full professor of theoretical physics at ETH Zurich, one of the most prestigious technical universities in the world. His doctoral work under computer scientist Ueli Maurer, completed in 2005, introduced the security framework for quantum key distribution that became foundational for the entire field of quantum cryptography. Google Scholar records approximately 27,000 citations across his career. He has won the ETH Medal, the ACM Best Dissertation Award, and the Golden Owl Teaching Prize from ETH Physics students, awarded twice in 2011 and 2017. He is not a speculative thinker, publishing provocative ideas to generate attention. He is an establishment figure at an establishment institution, working in the mathematical core of quantum information theory. Daniela Frauchiger was his doctoral student. She completed her PhD in 2016 with a thesis titled A Non-Probabilistic Framework for Scientific Theories. Her single blockbuster paper with Renner accounts for nearly all of her roughly 718 total citations on ResearchGate. And then she left. The ETH Group's alumni page notes that Frauchiger left science for a job in the real world. She now works at SIX, the Swiss financial infrastructure company that operates the Swiss Stock Exchange. The doctoral student co-authors a paper proving that quantum mechanics cannot consistently describe its own use, a paper that generates hundreds of citations and dozens of response papers and triggers an entire renewal of interest in the foundations of the theory. And then she walks away from physics entirely and goes to work at a stock exchange. I have thought about this a lot. I do not know Frauchiger's reasons. People leave academia for many reasons, most of them practical, and none of them anyone else's business. But there is something about the trajectory that echoes. It echoes Wigner reversing himself. It echoes the way certain problems in foundations seem to extract a personal cost from the people who confront them directly. The problems do not kill careers exactly. They just make it hard to continue standing in the room. Here is what Frauchiger and Renner proved, and I want to walk through the logic carefully because it is one of the most elegant and one of the most disturbing pieces of reasoning in modern physics. Their thought experiment involves 4 agents, 2 friends labeled F bar and F, sealed inside isolated laboratories, 2 super observers labeled W bar and W, who stand outside and can, in principle, measure the entire laboratories as quantum systems, friends included. The protocol works like this. At a specified time, agent F bar measures a quantum coin. This coin is not 50-50. It lands heads with probability 1/3 and tails with probability 2/3. Based on the result, she prepares a spin 1/2 particle. If the coin lands tails, she prepares the particle in the state called right arrow, which is a specific superposition of spin up and spin down. She sends this particle to agent F, who is in a separate, sealed laboratory. Agent F measures the spin of the particle. Now the super observers act. W bar performs a quantum measurement on the entire laboratory containing F. W performs a quantum measurement on the entire laboratory containing F. The structure deliberately echoes Hardy's paradox from 1992, but transplanted into a Wigner's friend setting, where the observers inside the labs are reasoning agents, not passive systems. The theorem proves that three assumptions cannot all hold simultaneously. First, universality. Quantum mechanics applies to everything, including macroscopic systems containing other observers. Second, consistency. If one agent uses quantum mechanics to determine that an outcome is certain, another agent is entitled to adopt that conclusion and reason from it. Third, single outcomes. Every measurement produces exactly one definite result. These three assumptions sound so reasonable, so basic, that it is hard to imagine giving up any of them. Universality says the theory applies everywhere. Consistency says agents can trust each other's quantum mechanical reasoning. Single outcomes says that when you measure something, you get one answer, not two. The trap snaps shut in 1/12 of all runs. In those runs, both super observers get a specific result. They label OK. But when you trace the chain of quantum mechanical reasoning backwards, you discover that W bar's conclusion about the coin disagrees with W's conclusion about the coin. W bar concludes the coin landed heads. W concludes it landed tails. Both used valid quantum reasoning. Both applied the three assumptions correctly. Both are certain, and they flatly contradict each other about a single past event. The coin landed one way. Two agents say it landed opposite ways. Both are correct according to the theory they are both using. At least one of the three assumptions must be wrong, and each interpretation of quantum mechanics escapes the trap by sacrificing a different one. Many worlds abandon single outcomes. The universe branches and both results happen. Copenhagen abandons universality. Quantum mechanics stops applying at some scale, and the lab is classical. Cubism abandons consistency. Your quantum predictions are yours, and mine are mine, and we do not get to combine them. The response from the physics community was heated. One anonymous reviewer admitted making 5 separate attempts to find an error in the calculations and failing every time. Matthew Leifer of Chapman University called it a thought experiment, which is going to be added to the canon of weird things we think about in quantum foundations. And Renner himself, in interviews, described his own interpretive journey as going from many worlds to cubism, to what he called no man's land. Some of his own graduate students reportedly refused to work on these problems, not because the mathematics was wrong, because the mathematics was right and the implications made them uncomfortable. I do not judge them for that, but I think it is worth noting that a mathematical proof about the foundations of physics produced a measurable psychological response in the people closest to it. These are not undergraduates encountering quantum mechanics for the first time and feeling overwhelmed. These are doctoral candidates at ETH Zurich, one of the finest physics institutions in the world, who looked at a valid mathematical proof about the internal consistency of their own field and said they would rather work on something else. That reaction tells you something that citation counts and journal impact factors do not. It tells you that the Frauchiger-Renner result lives in a category of knowledge that people prefer not to have. Not because it is speculative, not because it is uncertain, but because it is certain, and the certainty is about something nobody wants to be certain about. And here is a detail about the result that I think gets lost in the philosophical discussions. The contradiction appears in 1/12 of all runs. That is not 1 in a million. That is not a vanishingly unlikely edge case. 1 in 12. If you ran the protocol 12 times, on average, you would hit the contradiction once. It is not hiding at the margins. It is sitting in the middle of the probability distribution, where any experiment designed to test it would find it almost immediately. The paper generated over 30 published responses within 2 years. Physicists from multiple interpretive camps weighed in. Some tried to identify which assumption should be abandoned. Some tried to reinterpret the protocol, to dissolve the contradiction. Some argued that the theorem only applied to specific interpretations and not to their preferred one. But nobody found an error in the mathematics. 5 independent attempts by referees failed to find an error. The proof stands. Different interpretations escape the trap by sacrificing different assumptions. Many worlds abandon single outcomes. The universe branches and both results happen in different branches, so the contradiction is resolved by saying both conclusions are correct in their respective branches. Copenhagen abandons universality. Quantum mechanics does not apply to the macroscopic laboratories, so the super-observers cannot perform the measurements the protocol requires. Cubism abandons consistency. Your quantum mechanical conclusions are yours, and mine are mine. So the step where one agent adopts another agent's reasoning is not valid. Each escape works. Each escape costs something fundamental, and no escape is free, but a proof on paper is not the same as a result in a lab. Frauchiger-Renner had shown that the contradiction exists in theory. The question was whether you could construct a real physical setup where the observer disagreement was not just a logical exercise, but a measurable statistical fact. Whether you could build the thing, turn it on, and watch it violate a mathematical bound with enough statistical power to confirm that it happened. The theory's prediction is not just theoretical, it is physical. That question required a different kind of physicist, not a theorist who could manipulate abstract operators in Hilbert spaces, but an experimentalist who could build optical benches, align lasers, and collect 6-photon coincidence data for weeks on end. And it required a specific theoretical insight. The recognition that the Wigner's friend disagreement could be translated into the same mathematical language that had been used for decades to test quantum entanglement. That insight belonged to a physicist in Vienna who had been thinking about what facts are for longer than most of his colleagues were comfortable with. Časlav Brukner was born on July 9, 1967 in Novi Sad, then part of Yugoslavia. He studied physics at the University of Belgrade from 1987 to 1991, a period during which the country around him was disintegrating into ethnic war. I do not know the specific details of how the Yugoslav wars affected Bruckner's studies, but the timeline is hard to ignore. He was completing his undergraduate education in physics while the political order of his country was collapsing. He moved to Vienna. He earned his master's at the University of Vienna in 1995 and his doctorate at the Vienna University of Technology in 1999. And his doctoral supervisor was Anton Zeilinger. That name has already appeared in this story, and it is going to keep appearing because the threads in this narrative are not parallel. They are tangled. Zeilinger is the experimentalist who, alongside Alan Aspect and John Clauser, won the 2022 Nobel Prize in Physics for experiments with entangled photons. establishing the violation of Bell inequalities and pioneering quantum information science. He is the patriarch of the Vienna quantum optics tradition. He trained Brukner. He also trained Alessandro Fedrizzi. The people who would dismantle the assumption of observer-independent facts were trained by a Nobel laureate whose entire career was built on the prior generation of Bell test experiments. Experiments that assumed observer-independent facts were not in question. Brukner is now Professor of Quantum Information Theory at the University of Vienna and Scientific Director of IQOQI Vienna. He has accumulated approximately 23,000 citations across more than 220 publications. And in May of 2018, he published a paper that nobody outside of quantum foundations paid attention to, and that quietly changed the rules. The paper was called A No-Go Theorem for Observer-Independent Facts, published in Entropy, Volume 20, Number 5, Article 300. And what Brukner did was recognize something that should have been obvious in retrospect, but that nobody had seen before him. He saw that the Wigner-Friend disagreement could be recast as a Bell inequality. To understand why that matters, you need to understand what Bell inequalities are and what they test. And I need to correct a misconception here that even physics enthusiasts tend to hold. Bell's theorem is not about proving the universe is non-local. It is about proving that the universe cannot have a specific combination of properties simultaneously. John Stuart Bell published his original theorem in November 1964 in a journal called Physics Physique Physica, Volume 1, Issue 3, pages 195 through 200. He chose this journal because it paid its authors rather than charging page fees. The journal folded a few years later. The theorem it contained would eventually win 3 other physicists the Nobel Prize. Bell's theorem proved that if the universe is locally realistic, meaning if distant events cannot instantly influence each other, and if particles have definite properties before measurement, then certain statistical correlations in experiments with entangled particles must satisfy a mathematical bound. The correlations must be less than or equal to a specific number. Quantum mechanics predicts that experiments will violate this bound. The CHSH inequality, published by Clauser, Horn, Shimony and Holt in Physical Review Letters in 1969, put Bell's insight into an experimentally testable form. A certain quantity S, calculated from correlations between measurements on entangled particle pairs, must satisfy S less than or equal to 2 if local realism holds. Quantum mechanics predicts violations up to 2 times the square root of 2, approximately 2.83. Clauser and Stuart Friedman ran the first Bell test at UC Berkeley in 1972. Aspect closed the locality loophole in Paris in 1982 by switching measurement settings while photons were in flight. In 2015, 4 independent groups performed loophole-free Bell tests. In October 2022, Aspect, Clauser, and Zeilinger received the Nobel. In his banquet speech, Aspect noted that the recognition should go first to John Stuart Bell, without whom none of them would have been there that evening. Bell had died in 1990 of a sudden cerebral hemorrhage. At 62, he never saw the Nobel. That is the standard history of Bell tests. They proved the universe is not locally realistic. Particles do not have predetermined properties that exist independently of measurement. That was alarming enough to keep physicists arguing for decades. But Brukner did something different. In the standard CHSH inequality, The three assumptions being tested are locality, freedom of choice, and realism, meaning particles have definite pre-existing properties. Brukner replaced the third assumption. Instead of realism, he inserted observer independence, meaning measurement outcomes are facts that all observers agree on. The mathematical structure remained the same: S less than or equal to 2. If the inequality is violated, at least one of the three assumptions must be false. But now the three assumptions were locality, freedom of choice, and observer-independent facts. And quantum mechanics, applied to a Wigner's friend scenario, predicted a violation. Think about the shift that represents. Standard Bell tests asked whether particles have secret properties. Bruckner's inequality asked whether facts the same for everyone. The first question is about the microscopic world. The second question is about the foundations of science itself. Because if this inequality is violated, it does not just mean quantum mechanics is strange. Every physicist already knew that. It means the assumption underneath every lab notebook ever written, that what you measured is what happened, and it happened the same way for every possible observer, has a crack in it. And cracks in physics do not stay small. At some point around this time, there was a confrontation. At the conference, Zeilinger reportedly challenged Brukner directly on the implications of his work. The exchange, as described by people who were present, was not the polite academic disagreement you see in published response papers. Zeilinger declared, "The measurement apparatus is classical." I want you to hear what that sentence really means. The man who spent 40 years proving that quantum mechanics violates our intuitions about reality was now insisting that somewhere, at some scale, quantum mechanics stops. That there is a boundary between the quantum and the classical. That the measurement apparatus, whatever that is, sits on the safe side of that boundary. John Bell had a name for this idea. He called it the shifty split, the boundary that every version of Copenhagen needs but nobody can find, the boundary that moves depending on who is measuring and what counts as an apparatus, and how hard you squint. Bell despised the shifty split, and now Zeilinger, Bell's intellectual heir, the man who won the Nobel for vindicating Bell's theorem, was defending it against his own student. The experiment that would test Bruckner's inequality was already being built 400 miles to the north by another of Zeilinger's former students, in a photonics lab at a university named after a goldsmith and a steam engine inventor. Heriot-Watt University sits on the Riccarton campus on the western edge of Edinburgh. It was founded on October 16, 1821, as the School of Arts of Edinburgh, the world's first mechanics institute. It was designed to bring scientific knowledge to working people, named after George Heriot, a 17th century goldsmith who endowed schools for orphans, and James Watt, whose improvements to the steam engine powered the Industrial Revolution. It received university status by royal charter in 1966. It is not Oxford. It is not Cambridge. It is not MIT. And that matters to the story, because the experiment that tested whether facts are observer independent did not emerge from the most famous laboratory in the world. It came from a comparatively modest photonics facility in Scotland, run by a physicist who had left the Vienna epicenter to build something on his own terms. Alessandro Fedrizzi is an Austrian physicist who completed his PhD under Zeilinger at IQOQI Vienna in 2008. He spent 7 years at the University of Queensland in Australia, then joined Heriot-Watt in September 2015 as associate professor, later becoming professor of quantum physics. His research group is called the Edinburgh Mostly Quantum Lab, which tells you something about the culture he built. The name suggests people who are serious about the physics and not serious about the hierarchy. Massimiliano Proietti, the lead author, was an Italian doctoral student from Sapienza University of Rome. He came to Edinburgh to work with Fedrizzi and would complete his doctorate in 2020. After graduation, like Frauchiger, he left academia. He now works at Leonardo Labs, the quantum technology division of Leonardo SpA, Italy's major defense and aerospace company. And now I need to walk you through the experiment itself, because the specifics matter. This is the kind of experiment where the devil is in the details, and the details are what make it convincing. The team needed to do something that sounds straightforward and was anything but. They needed to create a situation where two observers each establish a fact about a quantum system and then test whether those facts are consistent. The experiment used 3 entangled photon pair sources designated S0, SA, and SB. Each source was a Sagnac-type interferometer, a ring-shaped optical path that generates pairs of photons entangled in their polarization states. The photons had a wavelength of 1550 nanometers in the telecom band, which matters because detectors in that range have the highest efficiency. They were generated by pumping a nonlinear crystal with a pulsed laser. The pump laser was a titanium sapphire system operating at 775 nanometers with pulses 1.6 picoseconds wide, running at a repetition rate of 80 megahertz. The repetition rate was effectively quadrupled to 320 megahertz using temporal multiplexing, a technique where delayed copies of the pulse are recombined to increase the rate of photon pair production. Each source contained a 22mm long, periodically poled potassium titanyl phosphate crystal, abbreviated PPKTP. This crystal performs type 2 spontaneous parametric down conversion, a process where a single pump photon is converted into a pair of entangled photons with orthogonal polarizations. The pump power was kept to 100 milliwatts, low enough to suppress the production of multiple photon pairs in a single pulse, which would corrupt the entanglement. The friends in this experiment were not people. They were photonic systems that performed a specific function. Type 1 fusion gates built from polarizing beam splitters and wave plates performed non-destructive polarization measurements on photons from source S0. The result of each measurement was recorded in the polarization state of an ancilla photon. This polarization state was the friend's memory. The paper defined an observer with deliberate minimalism as any physical system that can extract information from another system by means of some interaction and store that information in a physical memory. No consciousness required, no opinions about the mind-body problem, just a physical system that measures, records, and stores. Alice and Bob, the 2 Wigners in the experiment, were the final measurement stations. Each had 2 possible settings. Setting A0 or B0 meant reading the friend's record directly, performing a measurement in the computational basis, which reveals what the friend measured. Setting A1 or B1 meant performing a Bell state measurement, interfering the friend's memory photon with the ancilla photon on a 50-50 beam splitter. This second type of measurement is what constitutes Wigner's own fact. It corresponds to Wigner treating the friend's laboratory as a quantum system and measuring it in a basis that does not commute with the friend's measurement basis. Source S0's entangled pair was rotated by a half-wave plate set at an angle of 7 pi over 16 radians, a specific angle chosen to maximize the expected violation of the Bell-Wigner inequality. The photons were detected by superconducting nanowire single photon detectors operating at roughly 80% efficiency. Coincidence events, meaning events where all 6 photons arrived at detectors within a narrow time window, were identified by an FPGA-based timing system with a coincidence window of 1 nanosecond. The source quality was extraordinary. Entanglement fidelity was 99.62%. Concurrence, a measure of how much entanglement is present, was 99.38%. Bell state measurement fidelity was 96.84%. These are numbers that represent years of optical engineering. You do not achieve fidelity above 99% through luck or carelessness. And then they waited. Because the fundamental challenge of a 6-photon experiment is not building the apparatus. It is getting enough data. 6-photon coincidence events are extremely rare. Each individual photon detection has a probability well below 1. The probability that all 6 photons in the correct configuration hit their respective detectors within a 1 nanosecond window is vanishingly small. So the team ran the experiment continuously for 360 hours, 15 days, around the clock, collecting data point by point, coincidence by coincidence, slowly accumulating the statistics needed to say something definitive. They ended with 1,794 6-photon coincidence events, distributed across 64 measurement settings. And now, the result. The Bell-Wigner inequality says that if locality, freedom of choice, and observer-independent facts all hold, then a specific quantity S must satisfy S less than or equal to 2. The measured value was S equals 2.416, plus or minus 0.075. That is more than 5 standard deviations above the classical bound of 2, 5 sigma, the same threshold that announced the Higgs boson, the same threshold that, when applied to particle physics, triggered front-page headlines worldwide, triggered presidential comments, triggered Nobel Prizes. The paper's conclusion is stated with a precision that I think demands slow reading. If one holds fast to the assumptions of locality and free choice, this result implies that quantum theory should be interpreted in an observer-dependent way. If locality holds, if freedom of choice holds, then facts are not observer-independent. The experiment does not tell you which assumption to give up. It tells you that at least one of the 3 must go. And I want to spend a moment on each option, because the cost of each one is different, and the costs matter. Giving up locality would mean that distant events can instantaneously influence each other, not just in the EPR sense, where entangled particles are correlated in ways that defy classical explanation, but in a deeper sense, where the outcome of a measurement here can depend on what measurement was chosen there, regardless of the distance or the time between them. This would undermine the framework of special relativity, which says that no causal influence can travel faster than light. Virtually all of modern physics is built on that framework. Quantum field theory, the standard model of particle physics, general relativity, cosmology. Abandoning locality does not just change quantum mechanics. It threatens the coherence of every theory built on relativistic causality. Giving up freedom of choice would mean that the experimenter's decisions about what to measure were not actually free, that their choices were predetermined by hidden variables in a way that conspired to produce the exact correlations observed. John Bell called this superdeterminism, and it is technically a logical possibility. If the initial conditions of the universe were set up in precisely the right way, the experimenter's choices, the quantum system's state, and the measurement outcomes could all be correlated in a way that mimics a violation of the inequality, without any actual failure of observer independence. The universe would be, in effect, performing a cosmic magic trick, making it look like facts are observer-dependent, when actually everything was predetermined from the start. The problem with superdeterminism is not that it is wrong. The problem is that it is unfalsifiable. If the universe is conspiring to make every experiment come out in a way that looks like quantum mechanics, but is actually driven by hidden correlations we cannot access, then there is no experiment that could ever detect the conspiracy. Science itself becomes impossible, because every experimental result might be a product of the hidden correlations, rather than a genuine property of the system being studied. Bell himself considered superdeterminism and rejected it. He said, approximately, that if you could not trust the freedom of the experimenter to choose what to measure, you could not trust any experimental result about anything. The third option is the one the Proietti team pointed to. Give up observer-independent facts. Accept that the outcome of a measurement is a fact relative to the observer who performed it, not an absolute fact about the universe. This is the option that sounds the most radical, but that actually has the least collateral damage to the rest of physics. Locality is preserved. Freedom of choice is preserved. The theory works exactly as it always has. The only thing you lose is the assumption that everyone agrees on what happened. And that assumption, as I keep coming back to, is the one the scientific method was built on. The most parsimonious conclusion, the one the authors themselves point to, is that observer-independent facts do not exist at the quantum level. And the world's response was a brief spike of media attention, followed by silence. MIT Technology Review published a piece on March 12, 2019, headlined, "A Quantum Experiment Suggests There Is No Such Thing as Objective Reality." It went viral. For about a week, Live Science, phys.org, Science Alert, The Conversation. They all covered it. Fedrizzi and Proietti wrote their own accessible account for The Conversation, noting that the scientific method is founded on the reliable notion of observation and measurement, and that their result showed two different observers are entitled to their own facts. The attention lasted a few weeks. Then it evaporated. The expert response was revealing. Sean Carroll at Caltech objected, saying this was perfectly compatible with many worlds and nothing new. Tim Maudlin at NYU objected on philosophical grounds. Dustin Lazarevici published a paper called Keep Calm. Karen Crowther pointed out the observers were photons, not people. The community found ways to not deal with it. I want to say something direct about the consciousness objection, because I think it deserves friction rather than diplomatic balance. The argument that the Proietti experiment does not count because the friends are photonic systems rather than conscious beings is a retreat into exactly the kind of vague, undefined thinking that Wigner himself abandoned by 1987. The fusion gates extracted information from a quantum system. They stored it in a physical memory. The super-observer's measurement then erased that stored record through quantum interference. The physics of this process is identical whether the memory is made of photons or neurons. If you want to argue that consciousness is required, you need to explain where exactly the boundary between conscious and non-conscious observers falls. And you need to explain why that boundary should have any effect on the mathematics. Nobody has done this. Nobody has come close. The consciousness objection is not a scientific argument. It is a way to avoid confronting the result. I want to stop here for a moment and talk about what happened in the years between the Proietti result and the paper that deepened it. Because what happened, or more precisely, what did not happen, is part of the story. A significant follow-up came in 2020 from a team at Griffith University in Australia, led by Kok Wei Bong. Their paper, published in Nature Physics, Volume 16, pages 1199 through 1205, introduced what they called the local friendliness no-go theorem. This matters because it addressed a specific objection raised by philosopher Richard Healey. Healey had argued that the Proietti experiment relied on assumptions about the friend's measurement outcomes that were not justified in the quantum context, specifically that the friend's outcomes were predetermined before the super-observers measured. Bong and colleagues designed a scenario with weaker assumptions, deliberately avoiding the predetermination assumption, and still derived inequalities that quantum mechanics violated. In other words, even when you weakened the assumptions, even when you gave the skeptics more room to maneuver, the violations persisted. The walls around the result were getting higher, not lower. And yet, the broader scientific establishment treated the Proietti result not as a crisis, but as a curiosity. It was filed under quantum foundations, the subdiscipline that most working physicists regard with a mixture of polite interest and practical indifference. The result was discussed at specialized workshops attended by perhaps 100 people worldwide. It appeared in review articles read by a few thousand. It did not change the curriculum of a single introductory quantum mechanics course. It did not alter the research priorities of a single major funding body. It did not make a single physicist who was not already working on foundations rethink what they were doing. I spent time trying to understand why, and I think the answer is structural rather than individual. The incentive systems of modern physics are optimized for incremental progress within established frameworks. A graduate student who works on quantum computing will get grants, publications, and job offers. A graduate student who works on whether measurement outcomes are observer-independent facts will get polite nods at conferences and a very difficult career path. The machinery of academic physics selects for questions that fit inside the existing box. Questions that threaten the existence of the box get studied by specialists and ignored by everyone else. This is not conspiracy. I want to be clear about that. It is worse than conspiracy. Conspiracy requires coordination. This requires only inertia. The system was not designed to suppress uncomfortable results. It was designed to reward productive ones. And the definition of productive was set long before anyone imagined that the objectivity of facts might be an empirical question. The pattern has repeated itself across the entire history of quantum foundations. Bell's theorem was ignored for decades because the questions it asked were considered unprofessional. Bohr told people not to work on the measurement problem. Bohm's pilot wave interpretation was placed in a drawer in 1952 and left there. Everett was dismissed and left physics. The people who worked on foundations were not wrong. They were unfashionable. And in physics, as in every social system, unfashionable is a more effective form of suppression than wrong, because wrong gets debated and unfashionable gets ignored. First it was impossible, then when someone did it, it was trivial. The one thing it could never be was important. The Proietti result is the latest entry in that pattern. Not suppressed, not debated, ignored, filed, moved past. And then September of 2025 arrived, and the story gained another layer. A new paper appeared that made the problem worse, not by adding new experimental data, by showing that the disagreement between observers is not a glitch, it is not a fixable problem, it is a structural feature of the theory. And it has a name. Flavio del Santo, Gonzalo Manzano, and Časlav Brukner published a paper in Physical Review Research, Volume 7, Article 033-279, in September 2025. The title was Wigner's Friend Scenarios on What to Condition and How to Verify the Predictions. The concept at the center of the paper was information bubbles, and the concept is worse than the experiment, because the experiment could in principle have gone the other way. The 2025 paper shows that it was never going to go the other way. The theory demands the disagreement. Let me tell you about the people first. Flavio del Santo holds a Schrödinger Fellowship split between the University of Vienna and the University of Geneva, and he is affiliated with IQOQI, Vienna. He has published extensively with Brukner on Wigner's friend scenarios, including a 2021 paper in Communications Physics titled A No-Go Theorem for the Persistent Reality of Wigner's Friend's Perception, which showed that even the friend's experience of seeing a definite result is not guaranteed to persist once the super-observer acts. Del Santo also works on the history of physics, writing about Einstein, Bohm, and Karl Popper. He is the kind of physicist who reads the original papers from 1935 and finds things that everyone else missed, and then proves mathematically that the things he found matter. Gonzalo Manzano earned his PhD from Complutense University of Madrid in July 2017. He held postdoctoral positions at the International Center for Theoretical Physics in Trieste and at IQOQI Vienna in Bruckner's group from 2020 to 2021. That is where the collaboration with Del Santo and Brukner began. He is now a tenured researcher at IFISC, the Institute for Cross-Disciplinary Physics and Complex Systems at the University of the Balearic Islands in Palma de Mallorca. His background is in statistical mechanics and thermodynamics, which means he came to the foundations of quantum mechanics from the direction of information and entropy, rather than from the direction of particles and waves. Sometimes it takes someone from outside the usual foundations community to see what the people inside it have been too close to notice. The three of them, working within Bruckner's research orbit in Vienna, produced a paper that reframes the entire Wigner's friend problem. And the reframing makes things considerably more uncomfortable. Here is the standard telling of Wigner's friend, the version that has been repeated in textbooks and popular accounts, and even in this script up to this point. Wigner stands outside the lab. The friend is inside. The friend makes a measurement and gets a result. Wigner describes the lab as being in superposition. The implicit assumption in most discussions is that Wigner has the more complete description. He has what physicists call the view from outside. He sees the full quantum state. The friend only sees part of the picture. Del Santo, Manzano, and Brukner showed that this asymmetry is wrong. The situation is more symmetrical than it appears. The friend applies the collapse postulate, one of the standard rules of quantum mechanics, and obtains a definite post-measurement state. The friend's description of the world after the measurement is internally consistent, makes correct predictions about future measurements the friend might perform, and is a perfectly valid application of quantum theory. Wigner applies the Schrödinger equation, another standard rule of quantum mechanics, and obtains an entangled superposition state. Wigner's description is also internally consistent, also makes correct predictions about future measurements Wigner might perform, and is also a perfectly valid application of quantum theory. The two descriptions are flatly incompatible. One says the measurement produced a definite result, the other says it did not, and neither observer has access to any piece of information that would allow them to determine which description is correct. They cannot compare notes. They cannot step outside their own framework and evaluate it from a neutral perspective. There is no neutral perspective. There is no view from nowhere. They are trapped. The paper uses the term information bubbles, borrowing language from earlier work by Eric Cavalcanti at Griffith University. Each observer inhabits an information bubble. Inside each bubble, the description of reality is complete and consistent. From inside the friend's bubble, the measurement happened, a definite result was obtained, and the quantum state collapsed. From inside Wigner's bubble, no collapse occurred. The friend and the quantum system are entangled, and the outcome remains indefinite. Both bubbles are valid. Neither bubble has a privileged claim on what actually happened, and the boundary between bubbles cannot be crossed without physically performing a measurement that destroys the information in one bubble to create information in another. The paper goes further. It provides a framework for determining when and how observers can verify each other's predictions, when they can cross between bubbles by properly conditioning their predictions on available information. But these crossings come with constraints. The unrestricted reasoning that the scientific method implicitly assumes, where my result is a fact you can use and your result is a fact I can use, does not hold in general. The conditions under which one observer's fact can be meaningfully imported into another observer's description are limited and specific and depend on details of the experimental setup that determine the boundaries between the bubbles. I want to pause here and let the weight of this land properly, because it is easy to read past the implications when they are embedded in technical language. The 2025 paper is saying that quantum mechanics does not produce a single story about what happened. It produces multiple stories, parallel stories. Each story is told from inside an information bubble. Each story is internally consistent. Each story makes correct predictions within its own bubble. And there is no master story that reconciles them, no omniscient narrator, no God's eye view. The universe does not have a perspective. It has perspectives, plural, and they do not agree. This is not a metaphor. This is a technical description of a feature of quantum mechanics that the theory's own formalism demands. And the information bubbles framework shows something else, something that I think changes the character of the problem entirely. It shows that the Proietti experiment's 5 sigma violation was not an edge case or a loophole exploit or a quirk of the particular experimental design. The violation arises because quantum mechanics, applied consistently to observers who observe other observers, generically produces incompatible descriptions. The 2019 experiment found what it found because the theory predicts what it predicts. It was never going to go the other way. I need to pause here because I think the significance of that last point gets lost if you read past it too quickly. There is a difference between a result that surprises you and a result that the theory says is inevitable. The Proietti experiment could have been interpreted before the 2025 paper as a specific quirk of a specific experimental configuration. Maybe if you use different photon sources or different measurement bases or different entanglement structures, you would get a different answer. Maybe there was something about the particular setup in Edinburgh that produced a violation, and a different setup would have respected the classical bound. The Del Santo paper closes that door. The disagreement between observers is not an artifact of the Proietti setup. It is a generic feature of quantum mechanics applied to Wigner's friend scenarios. Any setup that physically instantiates the thought experiment, any configuration where one observer measures a system and another observer describes the first observer quantum mechanically, will produce incompatible descriptions. The specifics of the experiment are irrelevant. The structure of the theory guarantees the result. That is a different kind of problem. A violation that depends on a specific setup is a puzzle. A violation that the theory demands, regardless of the setup, is a feature of the theory, and a feature of the theory that contradicts the foundational assumption of the scientific method is not something you can file away in a subdiscipline and forget about. And here is where it gets worse, because quantum mechanics is, as far as anyone can tell, universal. There is no known scale at which it stops working. No experiment has ever found a violation of quantum mechanics. Not at the atomic scale, not at the molecular scale, not at any scale that has been tested. Decoherence, the process by which quantum behavior becomes effectively classical at macroscopic scales, does not mean quantum mechanics stops applying. It means that quantum effects become entangled with the environment so rapidly that they are practically unobservable. But practically unobservable is not the same as does not exist. The observer dependence that the Del Santo paper describes is there at every scale. At the macroscopic scales where humans operate, it is so thoroughly suppressed by decoherence that it might as well not exist. But might as well not exist is also not the same as does not exist. The Frauchiger-Renner theorem made this explicit. Their proof does not depend on photons or on any particular quantum system. It depends only on three assumptions, which are universality, consistency, and single outcomes. If quantum mechanics is universal, meaning it applies at all scales, and if measurements produce single outcomes, meaning you get one answer when you measure, and if agents can trust each other's quantum reasoning, then you get a contradiction. The contradiction is scale independent. It does not care whether the observers are photons or people. It cares only about the logical structure of the theory. This means the information bubbles are not confined to the quantum world. They are a feature of any situation in which quantum mechanics applies, which, as far as we know, is every situation. At the scales of daily life, decoherence makes the bubbles so perfectly overlapping that they are indistinguishable from a single shared reality. But the overlap is a practical consequence of size and temperature and environmental complexity, not a fundamental guarantee. The theory does not promise the overlap. It just makes it extremely likely for systems as large and warm and messy as human beings. Extremely likely, not certain. Now I want to survey what the major interpretations of quantum mechanics say about all of this, because the survey itself reveals something that I think is the most unsettling finding of all. The interpretations disagree about nearly everything. They disagree about whether the wave function is real. They disagree about whether particles have positions. They disagree about whether the universe branches. They disagree about whether consciousness matters. They disagree about whether quantum mechanics is about reality or about our beliefs about reality. But they agree on the data. They all agree that the Proietti result is what quantum mechanics predicts. They all agree the 5 sigma violation is correct. And they all agree that something has to give. The Copenhagen interpretation, the oldest and most widely taught version, traditionally invokes a boundary between the quantum world and the classical world. Below the boundary, particles obey quantum rules. Above it, measuring devices and lab notebooks and human beings obey classical rules. The measurement happens at the boundary. The wave function collapses at the boundary, and the location of the boundary is never specified. John Bell called this the shifty split, and he used the phrase with contempt. Where is the boundary? Nobody knows. Nobody has ever known. Is a photon detector quantum or classical? Is a computer that records detector clicks quantum or classical? Is a cat? Is a human? Copenhagen answers with deliberate vagueness. And in the Wigner's scenario, the vagueness becomes fatal. Copenhagen has to decide. Does the measurement happen when the friend measures or when Wigner opens the lab? If the answer is when the friend measures, then Wigner's quantum description of the lab is wrong. If the answer is when Wigner opens the lab, then the friend's experience of getting a definite result is not a real measurement. Copenhagen cannot answer this question without specifying where the boundary falls, and it was specifically designed to never specify where the boundary falls. The many worlds interpretation, first proposed by Hugh Everett III in his 1957 Princeton doctoral thesis, dissolves the paradox by denying that measurements have single outcomes. When the friend measures the quantum system, the universe branches. In one branch, the friend sees a flash. In another branch, the friend does not. Both branches are equally real. Wigner's superposition description is correct because the superposition is real. The friend in each branch experiences a definite result, but both branches exist. I want to tell you about Everett because his story is one of the most haunting in the history of physics, and it connects directly to the question of what happens to the people who look too closely at these foundations. Hugh Everett III was born in 1930 and wrote his doctoral thesis at Princeton under the supervision of John Archibald Wheeler. The thesis proposed that the wave function never collapses. Every quantum measurement causes the universe to split into branches, one for each possible outcome. All branches are equally real. We experience a single branch because we are embedded in one, not because the others ceased to exist. Wheeler arranged for Everett to visit Niels Bohr in Copenhagen in 1959. The visit was catastrophic. Bohr and his circle did not engage with the mathematics. They dismissed the entire framework. Everett later described the visit as a complete failure. Not a debate, a dismissal. He went into defense contracting, working on classified operations research for the Pentagon. He became wealthy. He ate and drank to excess. Colleagues from that era describe a brilliant man who had given up on the field that had refused his most important contribution. He died on July 19, 1982, at 51, of a sudden heart attack. His daughter Elizabeth found the body. She later described having barely known her father. He was a stranger occupying the same house. She believed in his theory. She believed that upon death, she would enter the branch of the multiverse where her father existed. On July 23, 1996, at age 39, she took her own life. In a note, she expressed the hope that she would join her father in a parallel world. I did not include that story to be sensational. I included it because the human cost of working on the foundations of quantum mechanics is not abstract. Everett's mathematics was correct. The many worlds interpretation is now the preferred framework of a significant minority of working physicists, including Sean Carroll, David Deutsch, and Max Tegmark. The man who created it never saw its acceptance, and the family he left behind was broken in part by his absence, and in part, grotesquely, by the very theory he had proposed. The pattern recurs. Bohm exiled, Bell unrecognized until after his death, Everett dismissed, Frauchiger departed. The people who confront the foundations pay a price that the people who build on the foundations never see. Sean Carroll's defense of the Proietti result relied on exactly the many worlds argument. There is no contradiction, because there is no single world in which the contradiction needs to be resolved. The price is an infinite proliferation of unobservable parallel universes. Sabine Hossenfelder has called belief in them equivalent to religious faith. Whether that comparison is fair depends on your tolerance for entities that exist only in the mathematics and can never be directly observed. And here is a detail about Everett that I think matters and that most popular accounts leave out. Everett proposed many worlds in his dissertation and was essentially laughed out of the room by Niels Bohr during a visit to Copenhagen in 1959. He left physics entirely. He went into defense contracting, working on classified military operations research. He became wealthy. He died in 1982 at 51 of a heart attack. His daughter, Elizabeth, found him. She later wrote that she had barely known him, that he was a stranger who had shared the same house. She believed she would enter his universe upon her death. In 1996, she took her own life. In her suicide note, she expressed hope of joining her father in a parallel universe. I did not include that story to be sensational. I included it because the psychological cost of confronting the foundations of quantum mechanics is not confined to abstract career decisions. Everett spent his life believing he had solved the measurement problem and that nobody would listen. The listening came decades too late, and the personal wreckage was real. Cubism, which stands for quantum Bayesianism, offers a different escape. Developed primarily by Christopher Fuchs at the University of Massachusetts, Boston, Rudiger Schack at Royal Holloway in London, and N. David Mermin at Cornell. Cubism holds that the wave function does not describe reality at all. It describes an agent's personal beliefs about what will happen when they interact with a system. Quantum mechanics is, in Fuchs's phrase, a single user theory for each of us. The probabilities in quantum mechanics are not frequencies of events in the external world. They are degrees of belief held by an individual agent, updated by experience, just as Bayesian probabilities are updated by evidence in classical statistics. Fuchs has been developing cubism since the early 2000s, and his writings on it have a distinctive literary quality that sets them apart from typical physics papers. He writes with a philosopher's attention to language and a kind of missionary intensity that suggests he believes he has found something important and is frustrated that the community has not yet caught up. The name itself was originally an abbreviation of quantum Bayesianism, but Fuchs later claimed the Q does not stand for anything or stands for itself. a rhetorical move that tells you something about the interpretive tradition he is working in. In cubism, the Wigner's friend paradox never arises because there is no objective wave function for the two observers to disagree about. The friend has beliefs. Wigner has beliefs. Their beliefs may differ. That is fine. There is no requirement that beliefs match. Measurement outcomes are personal experiences, not public facts. When the friend sees a flash, that is the friend's experience, not a fact about the universe. When Wigner describes the laboratory as being in superposition, that is Wigner's belief about what will happen when he interacts with the laboratory, not a fact about the laboratory. The elegance of this is that it dissolves every paradox in quantum foundations at a single stroke. There is no measurement problem because there is no objective wave function to collapse. There is no Wigner's friend paradox because there are no observer-independent facts to disagree about. There is no Frauchiger-Renner contradiction because agents cannot transfer their conclusions to each other as if they were objective facts. The price is steep. If the wave function is merely personal belief, then what is real? Cubism says the experiences are real. The measurement outcomes are real, but they are real for the agent who experiences them, not for the universe at large. Tim Norson has accused cubism of solipsism, the philosophical position that only one's own mind is sure to exist. David Wallace has called it a form of instrumentalism, a framework that uses the theory as a tool for making predictions without making any claims about what actually exists. The cubists deny both charges vigorously. Fuchs has written at length about how cubism is not solipsism because it posits a real external world that agents interact with, just one that the wave function does not describe. But the accusation persists because the framework genuinely struggles with a question that every working scientist takes for granted, namely, how do scientific communities converge on shared knowledge if the tool they use produces personal predictions rather than objective descriptions? I want to pause here and note something about the pattern that has emerged across all four interpretations. Each one resolves the Proietti result by giving up something fundamental. Copenhagen gives up universality. Many worlds gives up the uniqueness of outcomes. Cubism gives up the objectivity of the wave function. And relational quantum mechanics, which I will discuss next, gives up the observer independence of facts themselves. None of these sacrifices is trivial. Each one cuts into something that most physicists consider load-bearing. And the fact that there is no cost-free resolution, no interpretation that preserves everything while explaining the 5 sigma violation, is itself one of the most important results in modern physics. There is a phrase that I think captures the situation. It is not from a physics paper. It is from a philosopher of science named Tim Maudlin, and he said it in a different context, but it applies here with full force. In physics, it is considered bad form to ask, what is really going on? The Proietti result is the universe forcing that question on a discipline that has spent a century perfecting the art of not asking it. And then there is Carlo Rovelli's relational quantum mechanics. And I have saved this for near the end because I think it is the interpretation that sits most naturally with the Proietti result, and also the one that leads to the most uncomfortable conclusion about the scientific method. Carlo Rovelli was born on May 3, 1956, in Verona, Italy. He is an emeritus professor at the Centre de Physique Théorique de Lumini at Aix-Marseille University. He is one of the founders of loop quantum gravity, the principal rival to string theory as a theory of quantum gravity, and he is the author of 7 brief lessons on physics, The Order of Time, and Helgoland, books that have collectively sold millions of copies worldwide. Helgoland is particularly relevant here because it is, essentially, a book-length argument for exactly the conclusion the Proietti experiment reached. Published in 2021, it takes its title from the rocky island in the North Sea where Werner Heisenberg, sick with hay fever and unable to sleep, first worked out the mathematics of quantum mechanics in June of 1925. Rovelli uses that origin story to argue that quantum mechanics was relational from the very beginning, that the mathematics Heisenberg wrote down that sleepless night on Helgoland already contained the implication that physical quantities only have values relative to other physical systems, and that the entire history of the measurement problem is the history of physicists refusing to accept what their own equations told them. Rovelli has also credited LSD experiences in the 1970s during his student activist years in Bologna with sparking his interest in the nature of perception, consciousness, and time. He is not a conventional physicist. He does not write like one, and his interpretation of quantum mechanics is not conventional either. In 1996, Rovelli published a paper in the International Journal of Theoretical Physics, Volume 35, pages 1637 through 1678, titled Relational Quantum Mechanics. The paper's central argument was stated with a clarity that I think deserves to be heard without interruption. He wrote, "I suggest that the common unease with taking quantum mechanics as a fundamental description of nature could derive from the use of an incorrect notion, as the unease with the Lorentz transformations before Einstein derived from the notion of observer-independent time. I suggest that this incorrect notion is the notion of observer-independent state of a system. Read that analogy carefully. Before Einstein, time was assumed to be absolute, the same for everyone. It was so obvious that nobody questioned it. Then special relativity showed that time passes differently for different observers, depending on their relative motion. The notion of absolute time had to be abandoned. What Einstein did was not add something new to physics. He removed something old. He removed the assumption of absolute time, and the theory that remained was simpler, more elegant, and more correct. Rovelli is saying the exact same move needs to happen now. Remove the assumption of observer-independent states. Remove the assumption that quantum systems have properties independent of who is interacting with them. Just as velocity has no meaning except relative to a reference frame, quantum states have no meaning except relative to an observer. There are no absolute states. There are no absolute facts. Everything is relational. And just as removing absolute time resolved the contradictions that plagued Newtonian mechanics in the context of electromagnetism, removing observer-independent states resolves the contradictions that plague quantum mechanics in the context of measurement. In relational quantum mechanics, the Proietti result is not a crisis. It is a confirmation. The theory predicted exactly this. Of course, two observers can disagree about the outcome of a measurement. The theory says they will. The question Rovelli's framework raises is not how do we fix this, but something more subtle and more disturbing. How did we ever manage to believe that facts were observer independent in the first place? The answer, within relational quantum mechanics, is decoherence. At macroscopic scales, quantum systems become entangled with their environment so rapidly and so thoroughly that the observer dependence of facts becomes effectively invisible. Two scientists measuring the speed of light will agree not because reality requires them to, but because the decoherence is so overwhelming that the probability of disagreement is immeasurably small. The intersubjective agreement of everyday science is an emergent phenomenon, not a fundamental guarantee. It works, it has always worked, and it will continue to work at the scales where humans operate. But it is not a law of physics. It is a consequence of being big and warm and entangled with an enormous environment. The Proietti paper itself cited relational quantum mechanics as a compatible interpretation. The Stanford Encyclopedia of Philosophy notes that the Frauchiger-Renner result can be read as indirect support for RQM. The philosophical community has been paying attention to this even as the broader physics community has not. But there is a devastating objection to relational quantum mechanics, and it comes from a philosopher, not a physicist. Emily Adlam, working at the University of Cambridge, published a paper in 2022 titled, "Does Science Need Intersubjectivity? The Problem of Confirmation in Orthodox Interpretations of Quantum Mechanics." Her argument is precise, and it cuts deep. If each observer is trapped in their own perspective, Adlam argued, if there is no neutral ground from which to compare what different observers have found, then it is hard to see how we could ever have adequate empirical evidence for a theory like quantum mechanics. Science requires that different scientists perform experiments, share results, compare findings, and converge on shared descriptions of the world. That process of convergence, that intersubjective agreement, is not optional. It is constitutive of what makes science work. If observer-independent facts do not exist, then a foundation for this convergence is missing. And if the foundation is missing, then the theory that told us it was missing could never have been established in the first place. She was not saying relational quantum mechanics is wrong. She was saying something worse. She was saying that if relational quantum mechanics is right, we should not have been able to discover it. The theory, if true, undermines the epistemological framework that was necessary to confirm it. Think about the circularity. You use intersubjective agreement, scientists comparing notes, replicating experiments, publishing results that other scientists verify, to build the theory of quantum mechanics. And then that theory turns around and tells you that intersubjective agreement is not guaranteed by fundamental physics. The ladder you climbed to get to the conclusion says the ground you are standing on was never solid. Adlam's paper generated significant discussion. Cafaro and Hartman responded by arguing that the ideal of an observer-independent reality is not methodologically necessary for science, and that physics has taught us there is a limit to the usefulness of pursuing this ideal. This is a defensible position, but it is also, if you listen carefully, a concession. It is saying, yes, the assumption is wrong, but science can work without it. The question is whether that optimism is justified, or whether it is another form of the same comfort-seeking that has characterized the field's response to uncomfortable foundations results for a century. Rovelli took the objection seriously. In 2023, he and Adlam jointly introduced cross-perspective links as a new postulate within relational quantum mechanics. The idea is that information possessed by one observer is physically stored in variables accessible to other observers, providing a bridge between information bubbles that makes intersubjective agreement possible, even in a fundamentally observer-dependent world. Some commentators describe this as a major retreat from pure relationalism. Others described it as a natural development. The debate is ongoing. But the fact that the retreat was necessary, the fact that the most promising interpretation of quantum mechanics for handling the Proietti result needed to be supplemented with a new postulate specifically to preserve the possibility of science, tells you something about the depth of the problem. The interpretation that handles the data most naturally is also the interpretation that most directly threatens the epistemological foundations of the discipline that produced the data. That is not a coincidence. That is the shape of the problem. I want to do the consensus flip now, because I have walked you through 4 major interpretations: Copenhagen, many worlds, Cubism, and relational quantum mechanics, and they disagree about almost everything. They disagree about whether the wave function is real or merely a calculational tool. They disagree about whether the universe splits into branches or remains single. They disagree about whether consciousness plays any role. They disagree about the nature of probability. But here is what they all agree on. They all agree that the Proietti result is what quantum mechanics predicts. They all agree that the 5 sigma violation is real. They all agree that the standard assumption of observer-independent facts, in its naive form, cannot survive contact with the theory. And they all agree that the resolution, whatever it turns out to be, requires giving up something that most people consider essential. Either the universality of quantum mechanics, or the existence of a single world, or the transferability of one agent's conclusions to another, or the observer independence of facts. That agreement, the agreement across interpretations that disagree about everything else, is the part of this story that I personally find hardest to sit with, because it means the uncomfortable conclusion is not dependent on choosing the right interpretation. It is shared. It is structural. It is baked into the theory, and the theory is the most successful theory in the history of physics. Its predictions have been verified to more decimal places than any other scientific theory ever tested. Quantum electrodynamics, the quantum theory of the electromagnetic force, matches experiment to better than 10 parts per billion. The magnetic moment of the electron has been measured to agree with the theoretical prediction to 11 decimal places. No other theory in any field of science comes close to that level of empirical confirmation. This is the theory that is telling us observer-independent facts may not exist. This is not speculation from the margins. This is the central, most confirmed theory in science delivering a verdict about the nature of facts that its own practitioners do not want to hear. And now the question becomes, what does this mean for you? Not for physicists in their labs and their conference rooms and their workshops. For you, sitting there right now, listening to this, existing as a physical system that is extracting information from its environment and storing it in the electrochemical patterns of a 3-pound organ inside your skull. What does it mean for you that the most successful theory of physics does not guarantee that the facts you record are the same facts anyone else would record? I want to take this slowly because the answer has layers, and the layers matter. At the most practical level, it probably means nothing you will ever notice. Decoherence, the process by which quantum systems become entangled with their environments, operate so rapidly and so overwhelmingly at macroscopic scales that the observer dependence of facts is suppressed to the point of practical invisibility. The timescale for decoherence in a system the size of a human brain is incomprehensibly short, not milliseconds, not nanoseconds, somewhere in the range of 10 to the negative 30 seconds or smaller, depending on the system and the environment. By the time a single neuron has fired, the quantum coherence that would allow observer-dependent facts to manifest at the scale of your experience has been spread across so many environmental degrees of freedom that it is, for all practical purposes, gone. Two people watching the same sunset will see the same colors. Two chemists running the same titration will record the same endpoint. Two physicists measuring the charge of an electron will agree to as many decimal places as their instruments allow. Two astronomers pointing their telescopes at the same star will see the same photons. The intersubjective agreement that science depends on holds. It has always held, and it will continue to hold at every scale humans can directly access. That is not a guess. That is a prediction of the same quantum mechanics that produced the Proietti result. The theory is consistent. It predicts observer dependence at quantum scales, and it predicts the effective disappearance of observer dependence at macroscopic scales. Both predictions are correct. The question is what you do with the word effective. Effective disappearance is not the same as fundamental absence. The observer dependence does not go away. It becomes unmeasurable. It becomes so thoroughly diluted by the complexity of macroscopic systems that no experiment anyone could realistically build would detect it. But the theory says it is there, and the theory is the most precisely confirmed theory in the history of science. At a deeper level, it changes the character of that agreement. Every time you have read a scientific paper, every time you have trusted a replicated result, every time someone has said the data shows and you have accepted their conclusion, there has been an invisible assumption at work. The assumption that the data they collected is the same data you would have collected. That their measurement outcome is a fact about the universe, not a fact about their particular interaction with the universe. That the number in their lab notebook is a description of something objective, something that exists independently of the notebook and the person who wrote in it. The Proietti result does not prove this assumption is wrong at human scales. What it proves is that the fundamental theory of physics does not guarantee it. The guarantee was never there. It was assumed. It was assumed so deeply and so universally that no one thought to check. And when Brukner showed it could be checked, and Proietti checked it, the guarantee turned out to have been absent all along. But it holds, and it is guaranteed to hold by the fundamental theory of nature, are different sentences. The first is an empirical observation about how things have been. The second is a foundational claim about how things must be. And the foundational claim, as of September 2019, has a 5 sigma hole in it. The Proietti paper opens with a sentence that I have thought about more than any other sentence I encountered while researching this. The scientific method relies on facts, established through repeated measurements and agreed upon universally, independently of who observed them. After September 2019, after 1,794 6-photon coincidences in Edinburgh, after S equals 2.416 plus or minus 0.075, after 5 standard deviations of evidence against observer-independent facts, that sentence reads differently. It reads like an assumption that was never tested, an assumption that the theory of physics most comprehensively confirmed by experiment says is not guaranteed to hold. Think about what it means that we never tested this before. For 400 years, since Galileo pointed his telescope at Jupiter's moons and Tycho Brahe catalogued the positions of stars, the scientific method has rested on the assumption that the universe tells the same story to every observer. That assumption was so obvious, so taken for granted, that nobody thought to check it. It was like testing whether gravity works on Tuesdays. Why would you? Of course it does. Except in 2018, Brukner showed you could test it. In 2019, Proietti tested it. And the answer came back as not necessarily. The University of Vienna's Rudolfina magazine published a feature on April 14, 2025, timed to coincide with World Quantum Day, titled "When There Is No Reality Without Observation." It discussed the information bubbles framework as a significant advance in our understanding of observer-dependent facts. The coverage was measured, professional, confined to a university magazine with a specialized readership. It did not make the front page of anything. It did not trend on social media. It did not provoke a single presidential comment or a single prime-time news segment. And the reason it did not is that the implication is too large for the system to process. There is no existing institutional framework for absorbing a result that says the foundations of the scientific method are not guaranteed by the fundamental theory of nature. There is no grant committee for this. There is no policy response. There is no career track. And so the information sits in the literature, technically available to anyone who looks, practically invisible to everyone who does not. You are now someone who looked. I want to return to the human stories for a moment, because I think they carry a weight that the physics alone does not. Eugene Wigner asked the question in 1961. He spent the next 26 years gradually reversing his own answer. He decided that consciousness was not the solution. He decided that the problem was with the theory. He died in 1995 without resolution. The question outlived him. Daniela Frauchiger turned the question into a mathematical proof in 2016 and then left physics for the Swiss Stock Exchange. She proved that the most successful scientific theory in history cannot consistently describe its own use. And then she walked away. The proof is still there. She is not. Renato Renner followed the proof across every major interpretation and arrived in what he called no man's land. Some of his own students refused to work on the problem. Časlav Brukner built the mathematical framework that turned a 60-year-old thought experiment into a testable inequality and watched his own doctoral supervisor, a Nobel laureate, refuse to accept what it implied. Alessandro Fedrizzi, trained by that same supervisor, built the experiment in Edinburgh and got the 5 sigma result that confirmed what Bruckner's inequality predicted. Massimiliano Proietti, the lead author, the man whose name is first on the paper, completed his doctorate and went to work for a defense contractor. And Hugh Everett, who proposed in 1957 that the resolution was that the universe splits into branches at every measurement, was dismissed by Bohr, left physics, became a defense contractor, drank, died at 51, and had a daughter who killed herself hoping to find him in a parallel universe. The people who confront the foundations of quantum mechanics do not emerge unchanged. The problems they find are real, and the establishment's response to those problems is also real, and the personal cost is documented and specific. Not because the problems are controversial in the usual sense, not because anyone disputes the mathematics, but because the mathematics leads to conclusions that the practice of physics cannot accommodate without rebuilding its own foundations. And the foundations have not been rebuilt. The Proietti result is 6 years old. The Frauchiger-Renner theorem is 8 years old. The information bubbles paper is less than a year old. And the scientific method is still operating on the assumption that facts are observer independent. Nobody has proposed an alternative. Nobody has outlined what a science built on observer-dependent facts would look like. Nobody has explained how peer review works if your facts and my facts are not guaranteed to match. This is not because the problem is not recognized. It is recognized. Bruckner's 2018 paper has been cited hundreds of times. The Proietti result is discussed in every major quantum foundations textbook published since 2002. The problem is known. What is not known is what to do about it. I still do not know how to think about this. I am telling you that honestly, after spending more hours than I want to admit, reading these papers and their responses, and the responses to the responses, I do not have a clean answer to offer you. I do not think anyone does. The interpretive landscape is a maze with multiple exits, and every exit leads to a room you do not want to be in. If many worlds is right, there are infinitely many copies of you, each experiencing a different version of every quantum event, and none of you can verify the existence of any of the others. If Copenhagen is right, quantum mechanics is not universal, but nobody can say where it stops. If cubism is right, science is personal, and the convergence of scientific communities on shared knowledge is an unexplained miracle. If relational quantum mechanics is right, facts are relative, the scientific method assumed they were absolute, and the patch job required to restore intersubjectivity is still being sown. What I can tell you is this: the experiment was published. The result was 5 sigma. The theory predicts the result. The implication has been sitting in a peer-reviewed journal for 6 years with a clear and precisely worded conclusion, and the world moved on. You did not. You are still here. And that means you now know something that the vast majority of educated people do not. Not because it is secret, not because it is classified, not because you need special training to understand it, but because the implication is large enough and uncomfortable enough that the systems designed to communicate scientific results to the public would rather skip past it than explain what it actually means. The scientific method relies on facts, established through repeated measurements and agreed upon universally, independently of who observed them. That is the opening line of the paper that tested whether those facts exist. And the paper found, at 5 standard deviations, that the assumption may be wrong. Wigner asked whether 2 observers can agree on what happened. Frauchiger proved they cannot, within the theory. Brukner built the test. Fedrizzi ran it. Del Santo showed the disagreement is permanent. And the theory that told us this is the most confirmed theory in the history of science. It is not a fringe result. It is not contested mathematics. It is the output of the same formalism that gives you transistors and lasers and MRI machines and everything else that depends on quantum mechanics being correct. The 6 photons in Edinburgh did not prove that reality does not exist. They proved something more specific and more disturbing. They proved that reality, whatever it is, does not owe you agreement. It does not owe you consistency. It does not owe you a story that matches the story it tells the person next to you. The facts you gather, the measurements you make, the data you record, all of that is yours. It is real within your information bubble. It is internally consistent. It makes correct predictions, and it is not guaranteed to match what anyone else finds. Decoherence means you will almost certainly never notice. The practical machinery of science works. The bridge holds, But the theory that tells you why the bridge holds also tells you that the foundations underneath it are not what anyone assumed. And the people who know this best, the ones who built the theorems and ran the experiments and wrote the papers, have been sitting with this knowledge for years. They have not found a way to make it okay. Renner found no man's land. Frauchiger found the stock exchange. Everett found a bottle. Wigner found a reversal. I want to be honest with you about something. I have spent more hours than I want to admit reading these papers. The Proietti paper, the Frauchiger-Renner paper, Bruckner's no-go theorem, the Del Santo information bubbles paper, the Bonn local friendliness paper, the responses to the responses, the philosophical critiques, the counter-critiques, and at the end of it, I do not have a clean answer to give you. I do not think anyone does. The interpretive landscape is a maze with multiple exits, and every exit leads to a room you do not want to be in. If many worlds is right, there are infinitely many copies of you, each experiencing a different version of every quantum event that has ever occurred, and none of you can verify the existence of any of the others. If Copenhagen is right, quantum mechanics is not universal, but nobody has ever been able to say where it stops being valid. If cubism is right, science is personal, and the fact that different scientists converge on the same answers is an unexplained coincidence rather than a guaranteed feature of reality. If relational quantum mechanics is right, facts are relative. The scientific method assumed they were absolute, and the patch required to restore intersubjective agreement is still being sewn together. What I can tell you is what all of them agree on, and they agree on this. The 5 sigma violation is real. The theory predicts it. The naive assumption that facts are the same for everyone cannot survive contact with the formalism. Every single interpretation admits this. They just disagree about what to sacrifice. And that agreement, across frameworks that cannot agree on anything else, is the most important finding in this entire story, because it means the uncomfortable conclusion does not depend on picking the right interpretation. It is there in all of them. It is structural. It is baked into the mathematics of the most precisely tested theory in the history of science. So what does this mean for you? I want to take this slowly because the answer has layers and the layers matter. At the scale of your daily life, it almost certainly means nothing. Decoherence, the process by which quantum systems entangle with their environments, operates so rapidly and so overwhelmingly at macroscopic scales that the observer dependence of facts is suppressed to the point of practical invisibility. 2 people watching the same sunset will see the same colors. 2 chemists running the same titration will record the same endpoint. 2 physicists measuring the charge of an electron will agree to as many decimal places as their instruments allow. The intersubjective agreement that science depends on holds. It has always held, and it will continue to hold at every scale humans can directly access. But it holds, and it is guaranteed to hold by the fundamental theory of nature, are different sentences. The first is an empirical observation about how things have been. The second is a foundational claim about how things must be, and the foundational claim, as of September 2019, has a 5 sigma hole in it. Think about what that distinction means. For 400 years, since Galileo pointed his telescope at Jupiter's moons in January of 1610 and recorded what he saw in the expectation that anyone else with a telescope would see the same 4 points of light orbiting the same planet. The scientific method has operated on an assumption so basic that it was never stated, let alone tested. The assumption was that reality cooperates with science, that the universe, whatever else it might be, at least has the decency to tell the same story to every observer who bothers to look. That assumption is baked into every piece of the scientific enterprise. It is why we have peer review, because we assume that a reviewer replicating your experiment will get your result. It is why we have journals, because we assume that a fact published by one researcher can be used by another. It is why we have conferences, because we assume that scientists describing the same phenomenon from different laboratories are describing the same thing. It is why we have textbooks, because we assume that the knowledge accumulated by one generation of scientists can be transmitted to the next as objective knowledge about the world, not as the personal perspective of a particular set of observers. Every one of those institutions, every one of those practices rests on the assumption that the Proietti experiment tested, and every one of them continues to function, not because the assumption has been vindicated, but because decoherence makes the assumption true in practice, even though the theory does not guarantee it in principle. The floor holds, the building stands, but the foundation underneath it has a crack that the building's own blueprints say was always there. The engineers who designed the building did not know about the crack because they assumed the foundation was solid and never tested it. The test has now been done. The crack is real. And the building still stands because the crack, at the scale of the building, is too small to matter. But it is there, and the blueprints say it is there. And now you know it is there. That assumption was never part of any equation. It was never derived from any principle. It was taken for granted the way you take for granted that the floor will hold your weight when you step on it. It seemed so obvious that testing it would have felt absurd, like testing whether the laws of physics apply on Tuesdays. And then Brukner showed you could test it. And then Proietti tested it. And the floor held a 5 sigma crack. The University of Vienna published a feature in April 2025 about the information bubbles framework. It was measured, professional, confined to a university magazine. It did not make headlines. It did not trend anywhere. And the reason it did not is that there is no existing mechanism for absorbing a result like this. There is no grant committee for the scientific method's foundational assumption may be wrong. There is no policy response. There is no career track. There is no media template. And so the result sits in the literature, available to anyone who looks, invisible to everyone who does not. You are now someone who looked. I want to return to the people one last time, because the human thread in this story carries a weight that the mathematics does not, and the way it ends, or rather the way it does not end, matters. The timeline goes like this. 1961, Wigner publishes the thought experiment. 1987, Wigner reverses himself. 1995, Wigner dies without resolution. 2016, Frauchiger-Renner post the preprint that proves the contradiction is built into the theory. 2018, Brukner publishes the Bell-Wigner inequality that makes it testable, and Frauchiger-Renner appears in Nature Communications. 2019, Proietti runs the experiment, 5 sigma. 2020, Bohm closes the Healy loophole. 2022, Aspect, Clauser, and Zeilinger get the Nobel for the earlier generation of Bell tests, tests that assumed observer-independent facts were not at stake. 2023, Rovelli and Adlam patch relational quantum mechanics with cross-perspective links because the framework cannot preserve the possibility of science without them. 2024, Brukner's no-go theorem wins the Ehrenfest Prize. 2025, Del Santo, Manzano and Brukner show the disagreement is structural. Information bubbles. 64 years. From a thought experiment in a philosophical essay to a formal proof of structural observer disagreement. And at every step, the result was worse than the step before it. Wigner thought the problem was philosophical. Frauchiger-Renner proved it was mathematical. Brukner proved it was testable. Proietti proved it was real. Del Santo proved it was permanent. The people who carried this thread forward did not come out the other side intact. Wigner reversed his own most famous philosophical conclusion. Frauchiger left physics. Renner arrived in no man's land. Everett, who decades earlier proposed the most radical resolution, drank himself into an early grave while the physics establishment pretended his mathematics did not exist. His daughter followed him into death, hoping to find him in the branching universe he had proposed. Brukner watched his own mentor, a Nobel laureate, refuse the implications of his work. Fedrizzi built the experiment, and the world shrugged. Proietti published the lead author paper and went into defense. This is not a conspiracy against uncomfortable ideas. It is something more mundane and more persistent. It is the natural tendency of any institutional system to ignore questions it was not built to answer. The physics establishment was built to answer questions like, what happens when you collide these particles? And what is the mass of the Higgs boson? And how do you build a better quantum computer? It was not built to answer, are the facts you rely on actually observer independent? And so when that question was asked and answered, the system did what systems do when confronted with information they have no category for. It filed the answer and moved on. But the answer did not move on. It is still sitting there in Science Advances, Volume 5, Number 9, in Nature Communications, Volume 9, Article 37, 11, in Entropy, Volume 20, Article 350, in Physical Review Research, Volume 7, Article 33279, available to anyone. Read by almost no one. The most important result in the foundations of physics in the last 20 years, and the public has never been told. Until now, you have been told. The question that started in Budapest in 1961, in an essay by a man too polite to accept that his own thought experiment might be showing him something true, has now been answered by every tool physics has available. The mathematics says the disagreement is necessary. The experiment says the disagreement is real. The new framework says the disagreement is structural. And the sentence at the top of the Proietti paper is still there. The scientific method relies on facts established through repeated measurements and agreed upon universally, independently of who observed them. It has not been retracted. It has not been revised. It sits there like an epitaph for an assumption that the rest of the paper quietly dismantled. You are an observer. You are a physical system extracting information from another system and storing it in a physical memory. The neurons firing in your brain right now, encoding what you have heard, forming the electrochemical record of this conversation. All of that constitutes a measurement. And according to the most successful theory of physics ever constructed, the facts produced by that measurement are yours. They are not guaranteed to be anyone else's, not because of error, not because of imprecision, not because you misunderstood something, because the universe at its most fundamental level does not promise to tell the same story twice. It never did. We just never checked. Until 6 photons in Edinburgh in 2019 checked for us. And the answer, at 5 standard deviations, was the one nobody wanted.